Welcome back. You're here because you want to get up to speed quickly on the latest in AI research, right? Especially how we're making these large language models, well, smarter at complex reasoning.
Exactly. Without getting totally swamped in technical details.
Yes. So today we're diving deep into some really fascinating work. It's all about improving how LLMs handle tricky stuff, particularly mathematical reasoning.
And we're looking specifically at a recent paper, A Minimalist Approach to LLM Reasoning, from rejection sampling to reinforce.
That's the one. Our mission today, unpack its key findings. We'll focus on how, maybe surprisingly, simpler reinforcement learning methods are stacking up against the really complex ones.
Right. And we'll look closely at a method called RAFT, which performs unexpectedly well, and also dig into what this paper tells us about using negative samples, the wrong answers during training.
Okay, let's set the stage. For a while now, the go-to method for this kind of post-training fine-tuning, especially for math, has been something called PPO, Proximal Policy Optimization.
Yeah, you see it mentioned with big models like OpenAI's O1, DeepSeek R1. It's been pretty dominant.
The PPO is, well, it's complicated and computationally heavy, right? It needs this extra critic network.
It does. Adds overhead complexity, which is why there's this growing interest in simpler reinforced style approaches, things like Remax, RLOO, GRPO, Reinforce plus plus MO.
Because maybe all that complexity isn't strictly necessary for how LLMs generate text word by word.
That's part of the thinking. And this paper really zeroes in on two of these simpler paths, RAFT and GRPO.
Okay, RAFT, rejection sampling fine-tuning. You said it's basic. How basic are we talking?
Pretty basic. It's essentially a three-step loop. First, you collect data. You get your current model to generate, say, multiple different answers or solutions for each problem.
Like brainstorming different ways to solve it?
Kind of. Step two is data ranking, or the rejection sampling part. You use a reward function here. It's super simple.
Okay.
Correct is reward 1, incorrect is a 0.
Binary, yes or no?
Exactly. And you need something, a verifier, to tell you which answers are actually correct. You basically reject the incorrect ones and keep only the good stuff, the answers with reward 1.
Got it. So, generate options, keep only the winners. What's step 3?
Model fine-tuning. You take those selected correct answers, the positive samples, and you fine-tune the model specifically on them. The goal is just to make the model more likely to produce those good answers in the future. Equation 1 in the paper lays out the loss function for this.
Okay, so it learns directly from its own successful attempts. Is this similar to other methods out there?
It has similarities to STAR, the self-taught reasoner, but there are key differences. STAR often retrains from the original base model each time. RFT fine-tunes the current one. RFT generates multiple responses per prompt. STAR often just one. Little details, but they add up.
All right, so RFT sounds straightforward, maybe too straightforward. But here's the kicker.
It works surprisingly well.
Yeah. The paper shows RFT holding its own, even performing competitively on tough math benchmarks. They mentioned Math 500, Minerva Math, Olympiad Bench.
And compared to more complex methods, too.
Exactly. They give numbers for one model, Quen 2.5 Math 7B base. RAFT had about 49.9% average accuracy. That was better than an iterative DPO method, which got 48.2%, and honestly not that far behind PPO at 51.8% or GRPO.
Which is really counterintuitive, isn't it? Because standard RL wisdom says you need negative feedback. You need to learn from your mistakes. RAFT, in its pure form, mostly just learns from successes.
Right. It throws out the mistakes. So this brings up a huge question. How important are those negative samples, the incorrect answers, in this specific LLM context?
That's a central theme. So let's contrast RAFT with methods like GRPO or standard reinforce.
Okay. RAFT, mostly positives. GRPO reinforce use both positives and negatives.
Correct. They incorporate feedback from both correct and incorrect generated responses. And interestingly, the paper notes the performance gap isn't initially huge. RAFT can even converge faster early on.
Faster at first.
Yeah.
But maybe there's a catch.
There seems to be. The researchers did ablation studies tweaking the method to see what matters and found RAFT's fast start comes with a rapid drop in policy entropy. Figure 3 shows this.
Policy entropy, like how much the model explores different kinds of answers.
Exactly. High entropy means more exploration, more variety. RAFT, by focusing only on the right answers, quickly narrows down its options. It gets really good at producing those answers.
But maybe stops exploring other potentially good or even better reasoning paths.
Precisely. It reduces exploration. And that seems to limit its potential later in training. It hits the ceiling sooner.
Like cramming for a test by just memorizing specific answers. You ace those questions, but anything slightly different throws you off.
That's a good analogy.
Yeah.
And this lack of continued exploration seems to be why methods like GRPO, which keep exploring more, eventually pull ahead of basic RAFT.
Okay, so just using positive samples has a downside. What about the negative ones? Are all negative samples equally useful?
Apparently not. This is another key finding. Training on prompts where all the model's attempts were wrong. That can actually hurt performance significantly, especially for on-policy methods like standard reinforce. Figure 4 illustrates this.
So feeding it pure failure is actually bad.
It seems so. It might just confuse the model or lead it down completely wrong paths. Too much noise.
Ah, so it's not just whether you use negative samples, but maybe which ones? And this is where GRPO comes in.
Exactly. The paper suggests a big part of GRPO's advantage over standard reinforce isn't necessarily fancy algorithms, but that it implicitly filters out these prompts where everything generated was wrong. It avoids learning from that purely bad data.
Interesting. So GRPO is better partly because it ignores the really hopeless cases. Did they check other things, like how GRPO normalizes rewards?
They did. They looked at whether normalizing rewards within a prompt, adjusting based on the mean and standard deviation was a key factor. Minimal impact, apparently. Again, figure 4 supports this. The main benefit seemed to come from avoiding those all-negative prompts.
Okay, this is fascinating. It's really about the data selection, which led them to propose a new method, right? Reinforce-Rej.
Yes, reinforce with rejection. It's a really minimal change to the standard policy gradient approach, directly inspired by these findings.
Minimal how? What does it do?
It just adds a simple filtering step. It throws out any training prompts where the model either got all the generated answers correct or got all of them incorrect.
So it focuses only on the mixed bag prompts, where the model shows some understanding but still makes mistakes.
Exactly. The idea is to focus learning on the boundary, where the model is figuring things out, and the result. Reinforce-Rej performed comparably to the more complex GRPO in terms of final accuracy.
Wow. And it was more efficient.
Yes, better KL efficiency, meaning it learned more effectively for the computational effort involved.
So the big picture here seems to be that how you choose your training samples can be more critical than the complexity of the RL algorithm itself, at least in this context.
That's a major takeaway. It's more about principled sample selection than just, say, intricate reward shaping or complex policy updates.
But they didn't stop tweaking RFT itself, did they? They came up with RFT++-like.
Correct. They wanted to see if they could enhance the basic RFT idea.
And they added important sampling and clipping.
Yeah.
What do those do in simple terms?
Okay, so RFT keeps fine-tuning the same model. As the model improves, the data it generates changes. Important sampling is a technique to kind of adjust the learning signals to account for the fact that the data is coming from a slightly different, evolving model policy. It helps keep things stable.
Right, corrects for the moving target, and clipping.
Clipping basically puts limits on how much the model's policy can change in a single update step. It prevents large, potentially destabilizing jumps in behavior. Think of it like adding shock absorbers to the training process. Equation 6 shows the new loss function.
Makes sense. Smoother ride. And did RFT++ work better than plain RFT?
Yes, significantly better. Figure 1 and Table 1 show it converged faster and reached a higher final accuracy. For that same Quen base model, RAFT++ got up to 52.5% average accuracy.
That's a decent jump from RFT's 49.9% and now slightly edges out PPO's 51.8% in that comparison.
And they explicitly noted that the clipping part was crucial. An earlier attempt at RAFT++ without clipping actually performed worse than vanilla RAFT. So, stability matters.
But did RFT++ overcome that entropy collapse issue? Did it keep improving?
Not entirely. It still showed that pattern. Faster initial convergence, but then the improvement rate slows down, around iteration 100 in their plots, figure 2. GRPO, while slower initially, eventually surpassed RAFT++ in final performance in their experiments.
So even with the improvements, the reliance on only positive samples still seems to limit its long-term potential compared to methods that handle negatives more effectively.
That appears to be the case. The entropy still tended to decrease more rapidly than with GRPO.
Though they did add one more tweak to RFT++9, didn't they? Something called clip higher?
Ah, yes. That was an interesting detail. It's about making the clipping range asymmetric. It allows the probability of good actions to increase a bit more easily, while still strongly preventing large decreases or changes.
Kind of nudging it gently upwards while preventing big stumbles.
That's a good way to think about it. And this had seemed to help stabilize the policy entropy a bit more in later training and gave RAFT plus another small performance boost, as seen in Figure 2 on the right.
Okay, let's try and wrap this all up. What are the key takeaways for someone listening?
Well, first, don't underestimate simple methods. RAFT, despite being basic rejection sampling, is surprisingly effective for complex reasoning tasks. Maybe we don't always need the most complicated RL setup.
Right. And second, how we handle negative samples is really crucial. Just using all the wrong answers isn't necessarily good. Sometimes it's actively harmful.
Exactly. Which leads to the third point. GRPO's strength seems to stem significantly from its implicit filtering of poor quality samples, those prompts where the model fails completely, rather than just sophisticated reward normalization.
And RAFT++ shows that even with simple rejection sampling, incorporating techniques like importance sampling and clipping for stability and distribution correction can provide a real boost.
And finally, Reinforce-Rej offers a compelling alternative. A very minimal change, just filtering out the all positive and all negative prompts delivers strong performance very efficiently.
It really shifts the focus, doesn't it, towards smarter data curation and sample selection rather than just algorithm complexity.
Absolutely. The paper argues we need more principled ways to incorporate sample quality into training, rather than just assuming all negative feedback is helpful. RFT and Reinforce-Rej are presented as good, interpretable baselines for future work.
So here's a final thought to leave you with. Think about this beyond math problems. Where else are we fine-tuning LLMs with rewards? Coding, creative writing, dialogue systems? How could these ideas about sample selection apply there? What kinds of bad examples might actually be detrimental in those domains? Is simply getting a thumbs down always useful feedback for the model?
Yeah, it makes you really question how the quality, the diversity, and maybe even the difficulty of the examples we choose to train on fundamentally shape what these incredibly powerful models can ultimately do.
Lots to think about there. Thanks for taking this deep dive with us.